You know, when we talk about computing power, we usually focus on the big chips,
Right.
right? The CPUs, the GPUs, their speed.
Yeah, the processing cores get all the glory.
But what about how they, talk to each other, the connections between them? That's just as crucial for making all that power work together on, like, one really big problem.
Absolutely. And that's exactly what we're digging into today.
Today, we're doing a deep dive into a technology that's kind of an unsung hero there, NVIDIA NVLink.
That's right. We've been looking at some detailed research analysis covering NVLink, its architecture, its applications, where it's headed.
Okay.
And our goal really is to unpack that analysis for you, pull out the key insights, and understand why this specific piece of tech is so critical, especially for, well, the really demanding stuff like modern AI and high-performance computing.
Because the old ways, the traditional connections you might even have in your own PC, they can't keep pace anymore, can they?
Not even close. Not when you're dealing with the scale we see now.
We're talking training AI models with like trillions of parameters running these incredibly complex scientific simulations. The processors need to exchange just a massive amount of data super quickly.
Exactly. The sheer volume of data, the complexity of these models, things like large language models, it's putting, frankly, immense pressure on how components inside a system communicate.
And this is where the standard connections, like PCI Express or PCIe, start to really show their limits.
Right.
They're fine for general use, but when you've got multiple high-powered GPUs all needing to swap huge data sets constantly, PCIe can become the bottleneck, the slowest part of the chain.
It's like having a Formula One engine but trying to fuel it through a garden hose. The data just can't move fast enough between those powerful GPUs.
So speed and efficiency of that data exchange are absolutely key.
That's it. We're talking about bandwidth, how much data can flow at once, and latency, how quickly it gets there, the delay. Both are critical.
And this whole demand for better connections, it's not happening in a vacuum, right? It's a direct result of this huge shift towards parallel processing, using lots of processors, especially GPUs, working together.
Precisely. We've built these incredibly powerful accelerators, but if they spend all their time waiting for data from each other, you're not getting the full benefit. You're leaving performance on the table.
Okay, so let's unpack NVLink itself. What is it, fundamentally?
At its core, NVLink is NVIDIA's own proprietary high-speed interconnect. It's point-to-point.
Proprietary, so NVIDIA's design, point-to-point, meaning direct connections between things.
Exactly. And its main purpose, initially at least, was for communication between GPUs, GPU to GPU.
Right.
Though, as the research shows, there are specialized versions now that also handle high-speed links between CPUs and GPUs too.
So when NVIDIA first developed this, what were the main problems they were trying to solve? What were the big goals?
They had very clear objectives, based on seeing where things like PCIe fell short for multi-GPU setups. First, and maybe most importantly, significantly higher bandwidth.
Right.
They needed way, way more data throughput between GPUs than PCIe could offer for that specific job.
A much wider pipe, specifically for that GPU chatter.
Yes. Second, lower latency, less delay. When GPUs are working in parallel, they often have to wait for each other. Reducing that waiting time is crucial for speed.
So they can sync up faster, coordinate better.
Exactly. Third, improve scalability. How do you build systems with, say, dozens or hundreds of GPUs without the communication network just grinding to a halt? NVLink needed to make it easier for lots of GPUs to work together efficiently.
Let them team up effectively on bigger problems.
And fourth, enhanced power efficiency. Moving data costs energy. In big data centers, that adds up fast. NVLink aimed to be more efficient, moving more bits per watt.
So it's not just any connection. It's really optimized for NVIDIA's GPUs and these intense workloads, addressing the specific pain points of multi-GPU systems.
That's the key takeaway. It's highly specialized. It wasn't designed to be a general-purpose interface. It was purpose-built for the communication patterns you see in AI training and HPC.
Okay, let's talk architecture. How does it look different physically compared to using PCIe when, say, two GPUs need to talk?
Well, picture the traditional PCIe setup. If GPU A needs data from GPU B, that data often has to travel up to the CPU or maybe through a generic PCIe switch and then back down. It's not a direct route.
Kind of like sending mail through a central sorting office.
Yeah.
Adds delay, potential congestion.
Exactly right. NVLink changes that, at least for the GPU to GPU part. It provides direct point-to-point links between the GPUs, like having a dedicated high-speed pneumatic tube directly connecting them.
Direct lines. No middleman for that specific communication?
Yes. And the benefit is obvious. Drastically lower latency because the path is shorter and more direct and much, much higher bandwidth just for that GPU to GPU traffic. It shifts the focus from being CPU-centric to more GPU-centric for these parallel tasks.
And this direct link idea gets even more powerful when you bring in the NV switch, right? Creating what NVIDIA calls a GPU complex.
Correct. A GPU complex isn't just GPUs linked pairwise. It's a tightly integrated cluster of GPUs connected by NVLink, but orchestrated by this NV switch. The idea is that they function more like one giant unified processor.
So if NVLink is the direct road, what's the NV switch? Like a super efficient highway interchange just for those roads.
That's a great analogy. NV switch is a specialized chip, a super fast traffic controller designed only for NVLink traffic. And crucially, it's non-blocking.
Non-blocking meaning?
Meaning it can connect any GPU in the complex to any other GPU simultaneously at full NVLink speed. It enables what's called an all-to-all communication pattern, which is vital for many parallel algorithms where everyone needs to talk to everyone else quickly.
So not just direct pairs talking, but a whole group chat happening at full speed.
Precisely. It weaves all those individual NVLink connections into a single high-bandwidth fabric, and the NV switch itself has evolved incredibly fast. The latest one, for NVLink 5.0 with Blackwell GPUs, is a monster. 144 ports.
144 ports on one switch chip. What kind of total throughput are we talking?
That single chip handles 14.4 terabytes per second of non-blocking switching capacity.
14.4 terabytes per second. Wow. That scale allows for huge systems then.
Absolutely. The source mentions systems like the GB200 NVL72 using these switches to fully connect up to 576 GPUs. NVIDIA's goal, as they state it, is essentially to build a data center-sized GPU by linking hundreds of these together seamlessly.
And there's something called SHARP. What does that add?
SHARP, Scalable Hierarchical Aggregation and Reduction Protocol. That's a clever optimization. Certain operations are really common in parallel computing, like summing up values from all GPUs, a reduction operation.
Okay.
SHARP allows the NV switch hardware itself to perform some of these operations as the data flows through it.
So the GPUs don't have to spend cycles doing that reduction math. The network does it.
Exactly. It offloads that communication-heavy task into the network fabric, freeing up the GPUs and making those collective operations much faster. It's another layer of specialization for performance.
Okay, so we've got GPU to GPU covered with NVLink and NV switch. But you mentioned NVLink also connects CPUs and GPUs. Is that different?
It is. That's where NVLink chip-to-chip, or NVLink C2C, comes in. It's a specialized version designed for ultra-fast, very power-efficient connection between a CPU and a GPU, typically when they're packaged very closely together, like on the Grace Hopper superchip.
Right, the Grace CPU and the Hopper or Blackwell GPU talking directly via this C2C link.
Yes, and NVLink C2C has some really important features. First, the bandwidth is still huge, 900 GBps bidirectional between the Grace CPU and the attached Hopper or Blackwell GPU, much faster than PCIe for that specific link.
Okay, 900 GB is CPU, GPU, compared to the 1.8 TBs GPU with NVLink 5, both massive numbers.
They are, but maybe the killer feature of NVLink C2C is the coherent memory model.
Coherent memory, what does that mean practically?
It means the CPU and the GPU can see and access each other's memory directly and seamlessly, like it's one big shared pool. There's no need for the programmer to manually copy data back and forth between the CPU's RAM and the GPU's memory. The hardware handles keeping it consistent.
So the GPU can just read CPU memory, and the CPU can read GPU memory without explicit copies. That sounds like it simplifies things a lot.
Massively. It removes a major source of programming complexity and a potential performance bottleneck. And it leads to another big benefit: expanded GPU memory.
How so?
Because the GPU can directly access the large pool of system RAM attached to the Grace CPU, up to 480 gigabytes of LPDDR5X memory on Grace Hopper. This effectively extends the GPU's addressable fast memory way beyond its local high bandwidth memory, HBM. The source says up to 7x expansion.
Wow, so the GPU gets access to a much larger playground for its data.
Exactly. You can fit much bigger data sets, larger AI models, directly into this combined fast memory space, tackling problems that wouldn't fit in the GPU's own VRAM. And the C2C connection is incredibly efficient.
How efficient?
Compared to using a standard PCIe Gen 5 connection for that same chip-to-chip link on NVIDIA's silicon, NVLink C2C uses up to 25 times less energy per bit transferred and takes up 90 times less chip area.
25 times less energy. That's That's huge for data center power bills and cooling, isn't it?
Absolutely. For large-scale deployments, that kind of efficiency is critical for the total cost of ownership. This whole C2C design is really aimed squarely at AI and HPC workloads that need that tight CPU-GPU interaction without the data movement penalties.
And it still works with industry standards.
Yes. The underlying tech supports protocols like CXL and AMBACHI, which helps with interoperability.
Okay, this is all fascinating technically. High bandwidth, low latency, NV-switch, coherent memory. But let's talk impact. How does all this translate into real-world performance gains? Where does NVLink actually make a difference?
Right, this is where it really matters. These aren't just numbers on a slide. They enable fundamentally different capabilities.
Let's start with the obvious one, deep learning and AI model training. Everyone's talking about LLMs.
Exactly. The big challenge in training these massive models is that you split the work across many GPUs, right? But they constantly need to share information gradients, updated weights, activations. It's incredibly communication heavy.
The bottleneck we talked about earlier.
Precisely. NVLink, with its huge bandwidth and low latency, directly attacks that. By making the communication between GPUs much, much faster, it means the GPUs spend less time waiting for data and more time actually computing.
And the result is?
Significantly shorter training times. You can train these giant models faster.
So faster research cycles, faster deployment.
Much faster. And maybe even more importantly, it allows researchers and companies to tackle larger and more complex models than would even be feasible otherwise. Models that simply wouldn't train in a reasonable time on slower interconnects become practical.
You mentioned memory pooling before, too. How does that fit in?
That's a huge benefit enabled by NVLink in multi-GPU systems. It lets the system treat the combined memory of several GPUs as one single larger pool. This allows for things like larger batch sizes during training, which can improve efficiency. And critically, it lets you fit models that are simply too big for any single GPU's memory.
So it helps with those monster models that won't fit on one chip.
Exactly. It's also vital for model parallelism, where different layers of a neural network run on different GPUs. They need to pass results back and forth constantly and quickly. NVLink makes that efficient.
Do we have specific numbers showing this? Benchmarks?
We do. The source material points to the MLPerf training v5.0 results. NVIDIA's Blackwell systems, using NVLink 5.0 and the new switch, showed a 2.2x speed-up training, a huge Llama 3.1 405B model compared to the previous Hopper generation at the same scale.
2.2 times faster on a model that big. Wow.
And for fine-tuning a Llama 270B model, they saw a 2.5x speed-up using 8 Blackwell GPUs. Even for inference running the model, the NV-switch's high all-to-all bandwidth is crucial for serving large models quickly across multiple GPUs.
So, I mean, it sounds like NVLink isn't just helping with LLMs, it's almost enabling them.
You could definitely argue it's a co-enabler of the whole LLM revolution. Training models with hundreds of billions or trillions of parameters practically requires this kind of interconnect speed.
What about outside AI? High-performance computing, scientific simulations.
Very similar story there. Think about simulating climate change, fluid dynamics, complex molecular interactions. These often run across many GPUs.
Right.
And those GPUs need to exchange data constantly. Boundary conditions, particle positions, intermediate results. Again, high communication needs.
So NVLink speeds that up too.
Directly, leading to faster simulation results. Scientists can run more experiments, explore more parameters. And just like with AI, it lets them tackle larger, more detailed problems. Higher resolution climate models, bigger molecular systems, things that were just too slow or too big before.
And the unified memory, the coherent memory stuff helps here too.
Definitely. Unified memory simplifies coding complex simulations. And on Grace Hopper, that NVLink C2C coherent memory between the CPU and GPU is a massive advantage for codes that need both processors working tightly together without manually shuffling data all the time.
Any specific HPC examples?
The source mentions better performance in benchmarks like HPCG, which really stresses the interconnect, and speedups than molecular dynamics codes like AMBAR. And the raw specs for Grace Hopper are telling for HPC, that 3.4 TB's GPU memory bandwidth, nearly 500 gigabytes CPU memory bandwidth, plus the fast NVLink CTC link. It's built to move large scientific data sets quickly.
So pushing the boundaries of scientific discovery by enabling bigger, faster simulation.
That's the idea. And then there's professional visualization and rendering.
Like movie effects, architecture, product design.
Exactly. These pros work with absolutely massive 3D scenes, high-res textures, complex lighting. It pushes GPUs to their limits, especially memory.
How does NVLink help them?
Faster rendering times, for one. The source cites up to 50% reductions in some cases.
cutting render times in half. That's huge for production deadlines.
It really is, but maybe even more critical is the memory pooling, often called shared VRAM in this context. NVLink lets them combine the memory of multiple professional GPUs, like the RTX A series cards.
So they can load much bigger scenes.
Exactly. Scenes that would overwhelm a single GPU's memory. Without NVLink pooling, they'd have to rely on much slower methods, like constantly swapping data back to system RAM, which kills interactivity.
So it makes working with complex models smoother, more interactive.
Yes, much more fluid. It's key for things like real-time ray tracing, where artists need to see changes instantly. Better workflow, better results.
And standard software supports this.
Yeah, most of the major professional tools leverage it. The source lists Octane Render, V-Ray, Blender, Maya, Cinema 4D, Redshift. There's a benchmark mentioned from Puget Systems showing two RTX 6000 Ada GPUs with NVLink hitting almost perfect scaling, nearly 2x performance in Octane Render. That just wouldn't happen over standard PCIe.
And this is typically on the Pro cards, not the consumer GeForce ones, right?
Yeah. Correct. It really highlights its importance for those high-end workflows where maximum memory and performance are non-negotiable. It removes hardware bottlenecks for creative professionals.
Okay, to really appreciate NVLink, let's put it side by side with some other interconnects. How does it stack up?
Good idea. Context is important.
Let's start with the main one we've been contrasting against, NVLink versus PCIe. Sum up the key difference again.
Fundamentally, PCIe is the general-purpose connector for everything. NVLink is purpose-built, laser-focused on maximum performance for GPU to GPU, and, with C2C, tight CPU-GPU links within NVIDIA's ecosystem.
And the bandwidth difference for that GPU to GPU job is stark.
Extremely. NVLink 5.0 offers 1.8 TBs per GPU. A fast PCIe 5.0 by 16 slot gives you maybe 128 gigabytes effective bandwidth for a typical GPU to GPU hop that goes via the CPU or switch. So NVLink is potentially over 14 times faster for that specific critical path.
1.8 terabytes versus maybe 128 gigabytes. Okay, that's night and day.
It is. And latency is lower, too, typically 816 microseconds within an NVLink fabric node versus maybe 1525 microseconds or more for PCIe transfers between GPUs because of the extra hops. Plus, NVLink is generally more power efficient for moving that much data.
So PCIe for general stuff, NVLink for the super fast lane between NVIDIA GPUs.
That's the gist. They coexist, but NVLink handles the communication that would otherwise cripple performance.
What about CXL? Compute Express Link, that's built on PCIe, talks about memory too. How does it compare?
CXL is an interesting one. It's an open standard using the PCIe physical layer, focused on CPU to device connections, memory expansion, pooling, and importantly, coherency over PCIe.
So CXL is broader, more about flexible memory and device attachment using an open standard.
Yeah, CXL's goal is more around enabling composable systems, memory disaggregation across different vendors. NVLink, while it can support CXL protocols via NVLink C2C, is really about maximizing performance within NVIDIA's integrated platform, especially for GPU clusters and designs like Grace Hopper.
So, maybe more complementary than direct competitors, solving related but slightly different problems.
I think that's fair. CXL is pushing open standards for memory flexibility. NVLink is pushing the absolute performance envelope within NVIDIA's world.
Okay, and the other big player, AMD, has Infinity Fabric. How does NVLink compare there?
Right. Infinity Fabric is AMD's own proprietary interconnect. It's used pretty broadly in their ecosystem, connecting chiplets within CPUs, linking multiple CPU sockets, connecting CPUs to GPUs, and GPUs to GPUs.
So Infinity Fabric is maybe a more general-purpose fabric within AMD's architecture.
That seems to be the philosophy, yeah. A unified fabric across their products. NVLink's main focus has been that super high bandwidth off-chip GPU to GPU link, and now the specialized C2C CPU to GPU link. Different scopes, perhaps.
How do the GPU to GPU bandwidth numbers compare based on the source?
The source cites NVLink 5.0 at 1.8 TBs per GPU. For Infinity Fabric 3.0 and AMD's MI300X GPUs, the cited number for certain links is up to 576 GPUs. So on paper, NVLink 5.0 seems to offer significantly higher GPU to GPU bandwidth in NVIDIA's latest systems. Of course, real-world performance depends on many factors.
So both are critical proprietary interconnects for their respective companies, but designed with different specific priorities and architectural rules.
Exactly. Both are essential for enabling their high-end compute platforms.
It's clear NVLink didn't just appear fully formed, it's evolved really quickly.
Oh, dramatically. The pace of improvement has been relentless.
Take us through the generations quickly.
Okay, it started back in 2016 with NVLink 1.0 on the Pascal GPUs that offered 160 GPUs total per GPU. Then NVLink 2.0 with Volta in 2017 bumped that to 300 GPUs and, crucially, introduced the first NV switch.
Right, the switch was needed to build bigger multi-GPU systems.
Definitely. Then NVLink 3.0 with Ampere in 2020 doubled it again to 600 GPUs, along with NV Switch 2.0.
Keeping pace with the A100 GPU.
NVLink 4.0 arrived with Hopper in 2022, hitting 900 BGBs per GPU, plus the NV Switch 3.0, which had 64 ports, enabling larger scale.
And the latest Blackwell generation.
That's NVLink 5.0 in 2024, a massive jump to 1.8 TBs per GPU. And paired with the new NVLink 5 switch, the one with 144 ports, allowing those systems connecting up to 576 GPUs with that huge 14.4 TBs total switching capacity.
It really is like a consistent doubling almost every generation, every couple of years.
That's been the clear trend, yeah. It shows how critical NVIDIA views keeping the interconnect ahead of, or at least in lockstep with, the GPU compute power increases. The interconnect can't fall behind.
So what's next? Just keep doubling the bandwidth? Or is there more to it?
Well, future architectures like Rubin and Feynman will no doubt increase bandwidth further, but a really interesting strategic move mentioned in the source is NVLink Fusion.
NVLink Fusion, what's that?
This is NVIDIA licensing the NVLink technology, the C2C version specifically, it seems, to partner companies. Names like MediaTek, Marvell, Fujitsu, Qualcomm are mentioned.
Licensing their core interconnect tech to others. That feels like a big deal. Why?
It seems to be about broadening the ecosystem. It allows these partners to build their own semi-custom chips, maybe specialized CPUs or accelerators, and connect them directly to NVIDIA GPUs using that super fast, coherent NVLink C2C interface.
So, enabling hybrid systems. Combining NVIDIA GPUs with partner silicon using NVLink as the glue.
Exactly. It could potentially establish NVLink as the high-performance interconnect standard for building these kinds of advanced heterogeneous systems, extending NVIDIA's reach and influence, and supporting their whole AI factories vision, where NVLink is the backbone.
So NVLink started as a solution to PCIe limits and has become this foundational piece of NVIDIA's whole strategy.
Absolutely. It's been crucial for the breakthroughs in AI training speed and scale, for pushing HPC simulations further, and for enabling visualization pros to handle incredibly complex data sets.
And it really underscores the importance of co-design, doesn't it?
Yeah.
Developing the interconnect right alongside the processor.
You have to. Otherwise, you create bottlenecks. The fastest chip in the world is useless if it's starved for data or waiting on communication. The interconnect is just as vital as the compute units themselves.
And looking ahead, as systems get more distributed, mixing different types of processors, these fast interconnects become even more critical to make everything work together as one cohesive unit.
For sure. NVLink's evolution and moves like Fusion show its position to be a key technology shaping what's possible in computing for the foreseeable future.
So here's something to think about. That speed limit. How fast processors can talk to each other. It's not just a technical spec. It actually defines the scope of the problems we can even try to solve computationally.
Right.
When you break through those limits, like NVLink aims to do, problems that seemed impossibly large or slow yesterday, maybe training that next generation AI model, or running a simulation that used to take years, suddenly become achievable.
It literally expands the frontier of computation.
Well, that was a fascinating look under the hood at the connections that power so much of modern AI and high-performance computing. Thanks for joining us to unpack NVLink.
My pleasure. It's a really foundational technology, enabling a lot of the progress we're seeing.
Keep exploring the tech that builds the future. We'll see you next time.